Well, I'm kind of on a roll now with these videos tonight, so I'm going to do one more. Give you some examples from section 3.8, which is about using tangent lines to approximate functions, or in other words, what we call sometimes local linear approximation. And hey, why don't we just go ahead and look at the calculator for a second. So if you got some curvy type of function like y equals, I don't know, say something like, how about x cubed minus x? It's a nice looking, oh, what kind of crazy window is that? Zoom 6. Back to standard window, please. Now let's zoom in a little bit. So there's a nice looking cubic function. Now let's say, I don't know, let's say we're interested like in this spot right here. I don't know if you knew that you could do this trick. If you move the cursor to there and then do zoom in again, it'll zoom in around that spot. So nice and curvy there. Let's zoom in again. Every time you hit enter, it'll zoom in again. There you can see it curving off to the side there. And let's zoom in again. And after a couple times of zooming in here, you start to notice that, gee, that looks awfully straight. I mean, I don't know if let's zoom in one more time. Ooh boy, that looks awfully straight. Well, our window here, where you can see here, we're way zoomed in, right? This is a tiny, tiny little piece of this function, but it's really indistinguishable from a straight line. And this is true for all functions. So if we wanted to approximate this x cubed minus x function somewhere around -1, where we are here, you might as well use the straight line because it's awfully close, right? And the closer you are to that point where you found the tangent line, the better your approximation is going to be. So let's do a little bit of some examples. I think the notes will happen in class, so I'm just going to go ahead and work some examples here in this video. So use a local linear approximation. I have to have a local linear abbreviation for that. I get tired of writing that. Let's call that LLA from now on. Local linear approximation for f of -0.9 if f of x is equal to, and since we just looked at that function there, let's do that, x cubed minus x. Well, sometimes they tell you where to find the tangent line, but sometimes you have to figure it out. We don't want to go finding tangent lines at relatively unpleasant numbers like -0.9. That wouldn't be very fun, especially not without a calculator. So let's do it. Let's think of some number that's near this, but nice, right? Can you see the quotation marks? A nice number. So I think that's pretty clear. So let's use the tangent line at x equals, very close to this is -1, right? So we'll find the tangent line at -1, and then we'll plug this into it because, hey, that's close to -1, right? So it should be like a pretty good approximation. Sometimes you're told this, and sometimes you have to figure that out yourself, but it's always like the nearest nice value. All right, so let's see. To find the equation for a tangent line, I need a point, which will be the point -1, comma, plugging in here. Let's see, -1 cubed is -1 minus -1 is 0. And you might remember that actually was 0 on the function we just looked at on the calculator. So there's my point, and then, I forgot to find the derivative. So the derivative of this is 3x squared minus 1. So that means my slope, when I plug negative 1 into this, 3 times negative 1 squared is 1, so 3 minus 1 is 2. All right, so in point slope form, I have y minus 0 is equal to 2 times x plus 1. And go ahead and write that in slope-intercept form. So there's the tangent line. Now, that means that I can go ahead and plug numbers that are near negative 0.1, this tangent line, and this graph are very close. So let me go ahead and illustrate that for you so we can get a visual. First, turn your calculator on. So there's my function. Here's the tangent line, 2x plus 2. I'm going to go back to the standard window. All right, so let's go ahead and zoom in one time. There's my tangent line, right, at negative 1. Now I'm going to zoom in a little closer to that. Okay, so you can see, like, I mean, depending on how you judge these things, I'd say from like about here to here, we've got a pretty dang good approximation, right? They're very close. And if we zoom in again, there's the curve, there's the tangent line. I mean, they're almost right on top of each other. And I bet if I zoom in one more time, you're not even going to be able to tell the difference between them. Barely. You can see at the edges it got a little darker there. It was like 1 pixel off. So when we're close, as long as we're close to negative 1, right? That's negative 1 right there. As long as we're close, then this tangent line gives us a pretty good approximation for this. So if you want to know what's f of negative 0.9, instead of plugging it in here and trying to cube negative 0.9, which is not the worst thing in the world, but this is easier, right? Plug it in here instead. You can use the tangent line. We're using the tangent line. And that's, let's see, negative 1.8 plus 2, or, sorry, this should be, right, this is not f of negative 0.9, it's the approximation that we get from the tangent line. So it's about 0.2. And of course, we can go back, just turn this one off, we can go back here to this function and find out, well, hey, second calculate, what is, ooh, why did it do that? Maybe because I'm so zoomed in. Let me go back to zoom 6. I'll try that again. So what is, what do we actually get? How close are we? It's, if you can see that, all right, the glare, yeah, there it is. It's 0.171, and we got an approximation of 0.2. Is that a great approximation? Well, it's close, but if we had gone even closer to negative 1, then we would get an even better approximation. And that's how this game works. I'm going to do 2 more examples for you. Here's one that the AP folks like, things like that, or things like this. They like to ask questions like this. This is like a table of values kind of version. So if f of 2 is equal to 5 and f prime of 2 is equal to negative 3, find the local linear approximation, or I should say use local linear approximation to find f of 2.1, something like that. Now, you don't have any function, but I think we have everything we need here, because look, f of 2 equals 5, that is a point, right? That's the point 2, 5. And f prime of 2 equals negative 3. Well, that's the slope. So very thinly disguised, they gave us all the information that we need. So let's go ahead and write the equation for our line. In point slope form, y minus 5 is equal to negative 3 times x minus 2. And since I'm going to be plugging in, I'm going to go ahead and get it in slope-intercept form. That's negative 3x. That would be positive 6 plus 5. That would be plus 11. Okay, so now instead of plugging 2.1 into the original function, which, hey, I can't do that because I don't have the original function, right? So I have to plug it in to the approximation. Negative 3 times 2.1 plus 11, and certainly they could, and I would expect that you could do this without a calculator. That's negative 6.3 plus 11, which is 4.7. There you go. Might be worth just kind of looking to help your intuition here. If f of 2 was 5, and we were looking for f of 2.1, like a little further over, and the slope is negative, well, that means the function is decreasing, right? So it makes sense that it's a little bit lower, right? And if you think about units of slope, if you go over 0.1, if the slope's negative 3, going over 0.1 would have to correspond to a run of 0.1, would have to correspond to a rise of negative 0.3, right? If the slope's going to be rise over run negative 3, and there you go. It's negative 0.3. It's 0.3 lower than that. So, happy days. One more, last problem. Use an appropriate local linear approximation to estimate. Oh, how about the square root of, how about the square root of 37? Well, what the heck does this have to do with what we've been talking about? This is what. Notice that 37 is close to another number that would be a very nice number to take the square root of, namely 36, right? Of course, the square root of 36 is just 6. So the square root of 37 is 6 point whatever. So what we have to do here is try to frame this question in terms of some function and its local linear approximation. Well, we're talking about square roots of things, so we're talking about the square root function. You could write it like that, but better for calculus to write it like that. That's our function. And the nice point, we're going to use the tangent line at x equals 37 is not a nice number to plug in here, but 36 is, and that's close to 37. So we're going to use 36 to find the tangent line and then plug 37 into that equation. Okay? You can pause that for a second and think about that if you want to. So, go ahead and find my derivative. So 1/2 x to the negative 1/2. And now I need to find the tangent line at x equals 36. So, what's the point? The point, I don't mean that in an existential quandary kind of sense. I mean, what's the point? It's 36, 6, right? 36 in here, and square root of that is 6. So there's our point. My slope is, I plug 36 in here. Okay, here you go. For those of you who don't like doing this kind of thing, you need to be good at this. 36 to the 1/2 is 6. That means square root. And the negative flips it over. So 36 to the 1/2 again is 6. Negative makes it 1/6 times 1/2 is 1/12. Okay, so in point slope form, y minus 6 is equal to 1/12 times x minus 36. And let's go ahead and do that in slope-intercept form. That's 1/12 x. Oh, this isn't going to be too terribly pretty, I guess, but let's see, 36 over 12. 6 goes into both of those. It's 6 over, oh, hey, just kidding, 12 goes into 36 3 times. So that's minus 3, and then add the 6 over here. So the tangent line is 1/12 x plus 3. So we're trying to figure out an approximation for the square root of 37. So instead of taking 37 and plugging it in here, which you could do with a calculator, but not very easily without, we're going to plug 37 into the tangent line to this at a nearby nice value. So that means the square root of 37 approximately 1/12 times 37 plus 3, which is 37/12 is 3 and 1/12 plus 3. So that's 6 and 1/12. And if you're familiar with your repeating decimals, you might happen to know that 6.083 repeating. All right, now let's check it with a calculator, see how close we were. So let's see, the square root of 37 is 6.0827, and we got 6.083 repeating. Not too shabby. It would actually be correct to the College Board's 3 decimal places, right? That would round to 6.083. Same thing. So good to 3 decimal places. How about that? So that's one of the things we can actually do with tangent lines, use them to approximate functions. Because it's always easier to plug a point into a line than it is into some crazy function, even the square root function.